All right, so we're going to start with 1.1 material, which is about systems of linear equations. Now, as far as systems of linear equations goes, we want to first start off with like what is a linear equation. Most of us know this already, so this should be pretty review. A linear equation is an equation that can be written like this: a1x1 plus a2x2 plus so on and so forth, an xn equals b. All right, where these a's are going to be real numbers, generally speaking. These x1s, x2s, xn's are our variables. Now, notice that in linear algebra, most of the time our variables are going to be subscripted. Just because we run out of variables, we deal with a lot of variables. So if we start using like x, y, and z, we run out of those variables pretty quick. So we tend to use subscripts rather than using different letters to denote different variables. So x1 just means my first variable, x2 is my second variable, so on and so forth. Xn is my nth variable. So coefficients are the a's, variables are the x's, and then b is just a constant on the end. Now, if you look at the following equations, we can decide which are linear and which aren't. Take a second just on your own to do that. Push pause on the video. All right, so hopefully you've pushed pause on the video and did that. If you haven't, go ahead and do it. But I want you to look at this first equation. First equation, we have an x1 and then an x1 squared. So because we have a squared component to one of our variables, it is not linear. So squared component, not linear. Here, like I said, our coefficients, 4x1 plus 7/8 x2. Our coefficients are real numbers. x1 and x2 are both to the first power. We have an actual equation, and therefore this one is, in fact, a linear equation. So the first one is not, because we had a squared term. The second one is a linear equation. Everything's to the first power. The third equation, we have an x1. Notice we don't see an x2. And then we have something with an x3. Now this is still a linear equation. If you go back to what the definition of linear equation, there wasn't any requirement that a1 or a2 had to be non-zero. So we can always put 0 in there. And if you wrote the x2 out, it would be sort of like having a 0 as a coefficient. Okay. This last equation, so in short, the third equation is in fact linear. This last equation is not linear. You can see we have 7x1 plus 8 over x2. Now, even though the variables are raised to the first power, this one is being divided, okay? So as far as this goes, because we're dividing, if I were to rewrite this in a way that puts it in the numerator, the exponent on it wouldn't be a 1, it would be a negative 1. Hopefully that makes sense. If you were to rewrite this fourth equation, it would be x2 to the negative first power if you put that x2 in the numerator. All right, so equations 1 and 4 are not linear. Equations 2 and 3 are in fact linear. Again, most of you probably have seen that before. Now we're going to go straight to a system of linear equations, which basically just means that we're going to have a bunch of linear equations together, okay? A collection of linear equations that we treat as one big object, okay? So for example, here is a system of two linear equations, okay? We have one line and another line. By the way, oftentimes I'll use the word lines. Linear equations in 2 dimensions represent lines. Okay, that's fairly well stood. By 2 dimensions, I mean 2 variables. All right. Now, if I have a system of linear equations, the goal of these of one of the main goals when we're given a system of linear equations is to find a solution to that system, or maybe even multiple solutions. So a solution to a system of linear equations, if we've dealt with basic algebra, we know that it is a list of numbers so that when you plug in those numbers into your variables, they make both equations true, or all the equations true, I should say. Okay, so each equation is true when I plug it in. So for instance, 2, 4 is an ordered pair. If we plug in 2 to x1 and 4 to x2, we're going to get 3 times 2 plus 5 times 4. That is going to be, in fact, give us 26. So it's going to make the first equation true. And then 2 minus 2 times 4 is going to make the second equation true as well. So when I plug in this ordered pair in for x1 and x2, it makes the first equation true, makes the second equation true. So 2, 4 is a solution to that system. Okay? So it has to make every equation true in order to be a solution. Now, one thing I want to mention about this is that if we're writing down our list of numbers, because I have denoted these subscripts here, x1, x2, whenever you write a list of numbers, you're going to associate this first number with your first variable. So x2 goes for x1, 4 goes for x2. And if I had 14 variables, the order that that list of numbers would be in is x1 comes first, x2 comes second, x3 comes third, and so on and so forth. So the list of numbers is in the order of the variables, okay, the variable subscripts. All right. Now, we're looking for solutions, and there's a very small, slight difference between the solution itself, or a solution, and a solution set. A solution set is a list of all possible solutions. All right. Now, in our example, in fact, we only had one solution. Okay. So the only solution is this ordered pair. Okay. So the set containing that one thing is the solution set. But there are going to be other systems where we could end up with lots of solutions. And so the set of all solutions may contain, for instance, infinitely many ordered pairs. All right, so the set of all solutions is a solution set. Generally speaking, when we have a system of 2 linear equations, we're looking for solutions. And we'll find out very quickly that when we have any amount of linear equations, and I treat that system of linear equations, there's only going to be 3 possible numbers of solutions in my solution set. Now, we can end up with the one solution case. That was like the case we just dealt with, right? This ordered pair was the only pair that made this system of equations work. So that's what's going to happen a lot of the times. Probably if you were in, a basic algebra class, the vast majority of times when you solved a system of equations, you wound up with one solution. And you've probably seen these other two types of solutions too, but probably not dealt with them as much. So one solution, again, that's most common in like a basic algebra class, but we also have these other ones, and these other ones are going to be more important once we get into the linear algebra into, our next few chapters. So the infinite case, the infinite number of cases of solutions, well, uh, that comes up, for instance, when we have two lines that are exactly on top of each other. So again, I'm thinking in the two-dimensional realm right now. If you have two lines that are right on top of each other, then you could end up with infinite number of solutions. When you go into 3 and 4 dimensions, there's lots of different ways to get infinite numbers of solutions. All right, so we have the one solution case, the infinite number of solutions case, and then lastly, there is a situation where there's absolutely no solutions. Okay, again, in the two-dimensional case, this is the existence of like parallel lines, but you can have no solutions in lots of other ways when you get into 3 and 4 and 5 dimensions. So again, think parallel lines in 2 dimensions. Hopefully that all makes sense. Okay, so like I said, the goal a lot of times is to find equivalent, or excuse me, is to find the solution to a certain system. Okay, and the way we're going to approach this is by creating equivalent systems and continually making equivalent systems until we get like x1 equals a number and x2 equals a number. All right. Now, equivalent systems are two different sets of linear equations. So two different systems of linear equations which have the same solution. So it turns out, again, this first set is the exact same um, pair of linear equations that we dealt with before. If you plug in 2, 4, both of these equations are going to be true. And it turns out if you check this, you can plug in 2, 4, and both of these two equations are also true. So this system is equivalent to this system. All right. Now, actually, what you'll see is that these systems have something in common. Well, have a number of things in common, but they're related in some ways. First, you'll notice that the same equation is the top equation in both sets. And if you look closely, if you think about adding the top equation to the second equation, 3x1 plus 1x1, you're going to get 4x1. 5x2 minus 2x2 gives you 3x2. 26 plus negative 6 equals 20. So I knew that this system was going to have the same solution as this one, because basically what I did is I replaced the second row with just a sum of these two equations. Okay, that's one trick for making equivalent equations. Okay, and so our goal is to continually use tools that we know that keep equivalent equations, so produce equivalent systems of equations, until we get into a spot where our equations are as simple as possible. There's something like x1 is equal to some number, x2 is equal to some number, and so on and so forth. That's as simple as it can be. and then those numbers become my solution. So let's go ahead and do that in this situation here. So it goes to beg the question of how do we solve this? And this is just a harken back to what we did, or what you probably did in some algebra class somewhere. We're going to use the addition method or the elimination method. Okay, so we're going to use the addition method or the elimination method, whatever people like to call it, and we'll go through that method, and we'll continually create a system of equivalent equations. Okay, I'm going to do this in a Microsoft Word so that I just have a little bit more copy and paste. So here are my two equations. Okay, if I want to use the elimination method, what I would first do is I would look at the coefficients. So in this case, we have a 3, we have a 5, we have a -1, we have a 3. Let's, since this is a negative and that's a positive, I'm going to eliminate the x2 first. So I'm going to take these equations, and what I'm going to do is I'm going to take 3 and -1. I'm going to multiply the 3, oops, excuse me, 3 times both sides of that top equation. Now, that's one of the tricks of the elimination method, is that multiplying by a constant is actually not going to change the solutions, right? If we're ever solving any equation, I can always multiply both sides by a constant, and that doesn't change the equation. Now, when I do that, that's going to create the following system. We're going to get a 9 for the coefficient of x1, a -3 for the coefficient of x2, and a 27 for my constant. After that, in order to eliminate the x2, all we have to do is add these together. Now, usually, when I add these two equations together, in the elimination method, we forget about the other equation. In other words, probably what you've been taught is to add these two things together and get 14x1 equaling 28. All right. However, when we want to create equivalent systems, well, if this one started with one line, I could end up with one line down here. But since this started with two different equations, this equation by itself doesn't suffice. So what we have to do is when we add these, we're going to replace one of the equations. Let's replace the second equation, and we're going to end up keeping the first equation as well. All right, so not only do we have, so we've basically kind of cut out this second equation and replaced it by this one where we got by adding the two equations together. Okay, now you could have replaced the top equation too. It would have been perfectly fine if you would have said, well, I want to replace the top equation with this one, and then my new equation is going to be, or my new system is going to include that 14x1, but it's also going equals 28, but it's also going to include my original second equation. All right, in fact, let's keep it that way. So that's equivalent. Now, how would we solve this top system? Well, just like this, multiplying by a non-zero constant keeps things the same. Dividing by a non-zero constant keeps things the same. So we'll divide both sides of that equation by 14. And what that will give us is a system of equations. Divide this by 14, divide both sides by 14. We get x1 is equal to 2. All right, so that gives us x1. Now, most of us have been taught, well, at this stage, what do? You plug in the 2 back into one of your original equations. And that's nice. We can do that. But it turns out that if we want to have a computer program this, it's easier to just continue with elimination and do another elimination step. So what I'm going to do is I'm going to do another elimination step and then replace this other equation here. Okay, here's how we do that. So first off, I want to eliminate the x1 from down here. So what I would do is I would take -5 times essentially both sides of this equation. Sometimes I shorthand it by just taking -5 times the entire equation. And that means -5 times x1, -5 times 2. That's going to yield -5 times x1 is equal to -10. Now if I add these two equations together, what I'll do is I will replace this second equation with the sum of the first plus the second. All right, so I add these two things together, -5x1 minus 10. I'm going to keep that one. And -5x1 plus 5x1 becomes 0. I end up with 3x2 is equal to -9. All right, and from this point, it's pretty easy. Divide by your constants. You end up with x1 equals 2 and x2 equal to -3. All right. And we could check that that solution, that ordered pair 2, -3, actually does in fact satisfy our original problem. All right, plug in -2, plug in 2 and -3. It should satisfy the first equation. Plug in 2 and -3, and it should satisfy the second equation too. All right, so that's the theory behind it. Notice the types of things we were doing. We were just basically doing the same sort of tricks over and over and over again. Multiplying one equation, both the left and the right hand side, by a constant number. Adding the two equations together. Multiplying by a constant number. Adding the two equations together. You know, the multiplying and dividing, same deal. You could either divide by -5 or multiply times -1/5. Divide by 3, multiply times 1/3. So it's that same trick over and over and over again. And at any time and place, there's one other trick that I really didn't utilize here because I didn't need to. At any time and place, I could have switched the order. I could have said, well, actually, I'd rather see this equation on top and this one on bottom, right? Switching the order of equations really doesn't make any difference, Multiplying equation by a constant doesn't make any difference. Adding equations together doesn't make any difference. All right? So that's how we would solve a system of equations, by repeating those elimination steps. Again, notice I'm not using the plug-in thing because I just want to use those same simple processes over and over and over again. And if I do it that way, then there's less, it turns out there's going to be less stuff if I'm going to have to program it on a computer or something like this. All right. Now, this is obviously a system of three linear equations, and we have three variables, but the process is still the same. Adding things together, eliminating variables, and so on and so forth. So what I'd like you to do is try this on your own. Push pause on the video, try this on your own. Try to use those processes of multiplying by constants, adding equations together, eliminating variables in order to solve this system. Right, hopefully you did that. Now, I will say there's a lot of different ways to do this. You can eliminate, x2s first. You can eliminate x3s first. You can do all kinds of different things. I'm going to show you one way to do it, or the way I did it. I'm going to show it fairly quickly, so hopefully it doesn't go too fast for you. If it does, obviously you can always slow down the video and go through it. Hopefully, also I don't make any mistakes my first go around. All right, so what I would do is I would look at these equations. I'm going to eliminate x1 first. So the way I do that is I'm going to take 4, oops, 4, oops, I'm not in there. There we go, 4 times that entire equation, including my constant, so multiply it times both sides. And then I'm going to add it to -4, or excuse me, to this equation here. When I do that, I'm going to replace this equation here. Now I'm going to do that all in one step. And as I do that, hopefully this becomes a little bit easier. So 4 times x1 minus 4x1 gives me 0 x1s. I'll delete that in just a second. 4 times -2 is 8 x2s. So -8 x2s plus 5 means that that coefficient of the x2s should be -3. Again, I'm multiplying the top equation and adding it to the third one, all in this one step. 4 times x3 plus 9 x3 becomes 13 x3s. 4 times 0 plus a -9 stays a -9. Okay. Now, I'm going to do one more thing. I'm just going to say, well, might as well, I multiplied this by 4, might as well just divide it by 4 in the same step. So I kept the first equation the same, and I replaced this third equation, or this third equation, I should say, with 4 times the first plus the original third equation. Okay, so that eliminates my x1s. All except for this very top equations. All right. So now let's take this one and let's eliminate the x2s. So I'll eliminate this x2 in the first equation. And what I'm going to do is I'm going to, actually let's copy and paste that one more time. We got bits. We can spend as many bits as we want. All right, so I'm going to take 1 times this second equation, and then I'm going to add it to the top equation. All right, I don't even have to write the 1 because 1 times anything is itself. But I do want to highlight the fact that the reason I'm doing that is to eliminate the x2 up here. So I'm going to take 1 times this guy and add it to this. What that's going to give me, well, when I add this together, that's going to become 0 x2s. I'll delete that in just a second. Negative 8x3 plus x3 becomes negative 7 x3s. And then 8 plus 0 is 8. All right, so we've eliminated x2 out of my top equation. Now I'm going to leave some space just so we can line things up nicely. Okay, so I've eliminated x2 out of this top equation. Now I'm going to eliminate x2 out of the bottom equation. This one's a little bit trickier, but it's still all right. It's perfectly fine. I'm going to take 2 times the bottom equation and 3 times the second equation. I'm going to add them together, and I'm going to replace the bottom equation. Okay, so this one takes a little bit computing, but 3 times 2x2, that's 6x2s minus 6x2s. You get 0x2s. I will write this down just a second. So let's kill that. So I'm going to keep the second equation the way it is, but I'm going to take 3 times the second equation plus the bottom equation, and that's going to replace this bottom equation. All right, so what we get is no x2s. 3 times negative 8x3 plus 2 times 13x3. That's going to take my calculator to do it. 3 times negative 8 plus 2 times 13 should give me a 2x3. So I get 2x3 is equal to 3 times 8 plus 2 times negative 9 is a 6. All right, let's line that up a little bit too, just so that we have it. Now, notice what's happening. All right, I've kind of eliminated in one way. I started by eliminating my x1s. So I've kind of eliminated this line up, down until I got an x1. Once I did that, I went to my next equation, and I've kind of eliminated until that's the only spot that I have x2s in there. And now this third equation, I'm going to eliminate this x3, and I'm going to eliminate this x3 using this third equation. Now, it's kind of nicer to deal with ones, so what I'm going to do right now is, well, my cursor's jumping so much. Sorry. So what I'm going to do now is, instead of having 2x2 minus 8x3 equals 8, I'm going to divide everything by 2, so I get 1 here. And instead of equaling 2x3 equals 6, I'm going to divide both sides by 2. So if I divide that second equation by 2, I end up with x2 minus 4x3 equals 4. If I divide that last equation, all the terms by 2, I get x3 equals 3. Okay? All right. Now it's going to be easy to eliminate. All right. Now I can eliminate really quickly. Coefficients of 1 are really nice to deal with. We'll learn that as we move on. All right. So what am I going to do? I'm going to take 4 times that third equation, add it to this second equation, and replace the second equation. And then I'm going to take 7 times the third equation, add it to the first equation, replace the first equation. Okay, what you'll notice is by doing that, since I don't have x2's here, that doesn't affect the x2. Since I don't have x1's, when I do that, when I add this equation times anything, not going to affect this x1 at all. Just the x3's and the constants. Or just so let's do the second equation plus the 4 times the third. This will be better. All right, so 4x3 minus 4x3, that gets rid of my x3's. 4 times 3 is 12. Add that to 4, 16. All right. Then I do the same thing with this first equation and the third equation. In this case, I have to multiply it by 7. 7 times x3 minus 7x3. Now we've eliminated the x3's. 7 times 3 is 21, plus 8 is 29. So if I've done this right, I just keep eliminating using that same trick, multiply a equation by a constant, add it to another equation, and replace it. Multiply equation by a constant, add it to another equation, replace it. Whenever I need to, I can make numbers nicer by multiplying or dividing an equation by a constant, and that just keeps getting nicer and nicer and nicer until all of a sudden we're left with x1 equals 29, x2 equals 16, x3 equals 3. And the solution would be the ordered triple (29, 16, 3). Okay, if you write x1 equals 29, x2 equals 16, x3 equals 3, that's fine too. But just again, I'm emphasizing the fact that when you write your solution as a list of numbers, you always start with x1, then x2, then x3. Okay, so that's how we solve a system of equations. Now, what we're going to do, if you had to do that by hand every single time, it's a little bit cumbersome. You know, all of these x1s, writing x1 down every time, writing x2 down every time, and all that stuff takes time. So what we do is we switch over to using matrices. Now, a matrix is not a complicated idea. A matrix is just an array of numbers. So for instance, we draw these, typically when you draw a matrix, you have brackets around it, and then we have these 6 numbers, 3, 4, 5, 6, 7, 8. This matrix happens to be a 2 by 3 matrix. What that means is there's 2 rows and 3 columns. All right, so a matrix is just an array of numbers, and typically it's always going to be some sort of rectangular array, and we're always going to say a matrix is, you know, A by B, where we have A rows and B columns. All right, a 2 by 3 matrix has 2 rows, 3 columns. Now, how does this relate to our system of equations? It's pretty straightforward. We can cut if we line everything up. So if we have a system of linear equations, then we can line up the x1s, line up the x2s, line up the equal signs, line up the constants. And if you do that, then we can write 2 different kinds of matrices. We can write what's called the coefficient matrix for this system. The coefficient matrix is just the matrix of the various coefficients on your variables. Notice that when we write this, it only makes sense when these things are lined up. So each column is going to represent one of our variables. And traditionally, we always do this where the first column is representing the variable x1. The second column is representing the variable x2. All right, so that's what's happening here. Coefficients, columns are representing variables, and each row represents one of the equations. Now, obviously, with the coefficient matrix, we don't have the equal to part over here. So the coefficient matrix takes into account just the coefficients. If we want to add the constant parts, then what we do is we create what's called the augmented matrix. The augmented matrix is exactly like the coefficient matrix, but we also add in the constant parts. So in this case, the 5 and the -10. Sometimes you'll see this augmented matrix with a little bit of a line there. Let me see if I can draw that black. So a lot of times you'll see augmented matrices written and they'll throw a line in here where um, where the equal sign is. Okay, so that's basically all that is. So why don't you go ahead and just create the coefficient matrix and the augmented matrix for this system of linear equations. Push pause on the video and go ahead and do it. All right, so first off, coefficient matrix should just have the numbers 3, -1, 5, and 3. And when you go ahead and do that, actually, let me just go and do that on a scrap. Coefficient matrix is going to be 3, -1, 5, and 3. And again, order is important when you write this. So we want to have things, again, all the x1s we want to have in column 1. All the coefficients of x2s we want to have in column 2. And augmented matrix, I don't have that the right size. Going to be very similar. By the way, I'm just typing this in Word, making it hopefully as easy as possible to get at. Augmented matrix is going to be a 2 by 3 matrix, 2 rows, 3 columns, and we're just going to write 3, -1, 9, and then 5, 3, 1. Okay, if you want to draw a little line between the coefficients and the constants, then you can go ahead and do that. Otherwise, it's just I tend not to. Just understanding that that's the augmented matrix is perfectly fine. Go ahead and do the same thing for this system of equations as well. All right, so hopefully that didn't take you too long to do. Again, if you haven't done that, push pause on the video and do it. But let's go ahead and just show you the exact, if you're doing the coefficient matrix, it starts out as 1, -2, 1. And then the second row is 0. Notice we don't have any x1s here, so we call that 0. And then 2, and then -8. And then -4, 5, 9 for a coefficient matrix. For our augmented matrix, it looks like that for the first 3 columns. looks the exact same as the coefficient. And then we add on this last column, which are the constant numbers, 0, 8, and -9 in this case. So that's our augmented matrix for this system of linear equations. Now, what we're going to do is I'm going to show you kind of what the elimination steps are doing to equivalent systems of linear equations and how that impacts an augmented matrix. So we're going to deal with coefficient matrices in later sections. Right now, we're going to look at the augmented matrix and sort of deal with that. All right. So let's go back to this example here. All right. And what we're going to do is we're going to use elimination on this system. And as we do that, we're going to see how that affects an augmented matrix that we're going to put right beside this system. Okay? So if you've been paying attention, this was the exact same system we just had a second ago. 3x1 minus 1x2 equals 9. 5x1 plus 3x2 equals 1. All right? So we're going to do this on a sort of side-by-side look. I'm going to try to do this. Hopefully this will be visible. There we go. Okay. So all right. So on the left, we have our system of equations. Now what we would do elimination-wise, we would have taken 3 times the top row. Oops. And we would have added it to the second equation. I say 3 times the top equation, added it to the second equation. And then we'll replace that second equation with that. Notice what that does over here. It's basically taking 3 times this top line, the top row, adding it to the second row, and we'll replace the second row. Okay? So as far as actually notation-wise, so I'm sorry, as far as notation-wise goes, the way we typically write this when we're dealing with matrices, if you're doing this freehand, is you'll write 3 right next to the top row, and then 2 lines out, because we're going to concern row 1 and row 2. Connect them, so 3 times the top row. Some people will put a 1 times the second row, and then we're going to replace that second row. All right, so that's what we're doing. That's typically the notation we do. 3 times the top row plus the second row, and then replace it, and then we'll get a new matrix. All right, so let's go ahead and do the linear system. What that would do, replacing this 3 times 3x1, that's 9, plus 5 gives me 14. 3 times -1 plus 3x2 gives me 0. 3 times 9 gives me plus 1 is 28. So there we go. So my new system would be that one. That's very similar to what we did earlier, right? In fact, these are the same equations. If I did that to the matrix, it's just a lot less writing. 3 times this, 3 times 3 plus 5 gives me 14. 3 times -1 plus 3 gives me 0. 3 times 9 plus 1 gives me 28. Okay? And then what would I do? Well, I would divide this by 14. The way we would do that, write that notationally over here on the matrix, is by taking either a divide sign, 14, or you'd write 1 over 14. This is hard to do with a mouse. And then replacing that. So notice there's just one arrow out. When we did this the first time, we had 3 and maybe 1, but the one's omitted, combining and replacing that second equation. Okay, so 1/14 times the second equation. Notice you're not messing with the first right now. So doing that over here, gives me x1 is equal to 2. Doing that over here gives me a matrix which just has a 1, a 0, and a 2. Divide that second row by 14. So you can see what's happening here. All of the things, all of the tricks we did to create equivalent systems over here are analogous to doing some sort of operation on the augmented matrix. Okay? Now from here on out, similar things. 3, whoops, thought I was on the right spot. 3 times the second equation, and then we're going to add it to the first over here. 3 times the second equation, add it to the first. And again, we're going to replace the first with that. All right. So that's how that would, or excuse me, I didn't want to do 3, did I? I wanted to use -3. I apologize. -3, -3. That way, that'll turn into a 0. So yeah, my apologies. -3 instead of +3. So we get an actual 0, x1, when we replace the first equation. So let's change that over here just so we can get the right thing. All right, so -3 x1 plus 3x1 gives me that. Notice there's no -3 times no x2s plus that. Just gives me that -1 x2 again. -3 times 2 plus 9. That's a -6 plus 9. That gives me a 3. So there's my two equations. I bet you know what we're going to do next. Go over here. Same thing. -3 times 1 plus 3 is 0. -3 times 0 plus -1 is -1. -3 times 2 plus 9 is 3. Okay. Now at this point over here, on the left-hand side, I would probably divide divide by -1 on the top equation. So I would just, do my standard divide by -1 on the top equation to give me x2 is equal to -3. Same thing over here. I'd multiply that top equation or divide it by -1, whichever way you want to see that. 1 equals 1x2 equals -3. All right. And just for the sake of notation, notice that these are kind of usually, I end up with x1 on the top and x2 on the bottom over here when I'm dealing with my equations on the left. So I can just swap those out, swap the order of them if I wanted to, take top equation and make it the second equation. Take the second equation, make it the first equation. Okay, nothing really is happening there other than swapping the order. By the way, if you do that with your matrix, the notation that we tend to get, you tend to see this notation next to the matrix. So you put row 1, put that in the second row 2, now swap it. So that's a row swap. And yeah, fairly easy what we're doing there. So let's go ahead and do that. Now, when you do this, notice what we have. Notice what kind of matrix we have. Okay. Once you get used to this matrix over here, you're going to see it as, oh yeah, x1, 1 times x1 is equal to 2. And 1 times x2, because remember those x2s always stood for that second column. x1s were always in the first column. Constants were always in the third. So you'll immediately see, oh yeah, first column 1x1 equals 2, 1x2 equals -3. Okay, so you'll be able to see the solution just as easy over here as you do over here. And once you've done it enough, you're actually will become, it'll become a lot easier, let's say, to do things with the matrix than it will be with the system of equations. Because with the matrix, you don't have to write down x1, x1, x2, x2 every time. And we'll see later on in this chapter that with computer programming, it's a lot easier to tell your computer to simplify a matrix than it is to come up with a bunch of linear equations. So it's easier to program with matrices too. Now, what we just did with all those matrices were what's called elementary row operations. Okay, so these elementary row operations on matrix translate into operations we did to create equivalent systems of linear equations. So we had the replacement. We take a multiple of a row and a multiple of another row, and we add them together and we replace one of the rows. All right, that's basically just saying a constant times an equation, add it to another equation. We could have swapped any two rows. That just means the order of the equations could have been flipped. And then scaling, multiply or divide a row by a constant. Now, that constant does have to be non-zero, because if you multiply things by 0, then everything goes away and you get all kinds of trouble. But any non-zero constant you can multiply by. All right. So if we continue to utilize those 3 elementary row operations, we can really simplify any matrix and get a solution to a system of linear equations. So the last thing we'll do in 1-1 is I'll have you try to simplify this, but instead of using the system of linear equations, only use that augmented matrix. So write this out as an augmented matrix, and then start using those elementary row operations until you get a solution to this system of linear equations. All right? Push pause on the video. It'll probably take you a while, and then I will come back and do that by hand. All right, so hopefully you've done that. If you haven't, again, make sure you pause the video and do that. I'm going to do this, show you how this is done, and same deal. So first off, We take the system of linear equations. Okay, we translate that into an augmented matrix. In this case, it's going to be 7, -5, 19, 4, 10, -2. Real quick, just everything that I give you pretty much is going to be lined up, but make sure you're checking your subscripts just in case, they don't have a 0 in there or something like that. So make sure you're diligent about that, but most of the things I give you are already lined up as far as the x2s are in the same sort of column and x1s are in the same sort of column. Okay. All right. Now, you can do this in a number of ways. What I am going to do is I'm going to create a 0 right where that 10 is. Okay, so what I'm going to do is I'm going to take 2 times the first row, add it to the second row, and replace the second row with that. Okay, so 2 times this, add it to that. So 7 times 2 plus 4, that's 14 plus 4 is 18. -5 times 2 plus 10 becomes 0. 19 times 2 minus 2 becomes 36. All right. So what do we got here? Say 19, 0, 36. Easier to deal with ones than it is to deal with, oh, excuse me, I didn't say 19, I said 18, didn't I? Whoops, I messed that up. So easier to deal with ones than dealing with 18s. So what I'm going to do is divide that second row by 18. So what I like to do is I like to just write 1 over 18. That doesn't look very good, but that's okay. Replace that second row. And 1 over 18 times 18 gives me 1. 36 times 1 over 18 gives me 2. So we can use that elementary row operation and get a 1, 0, 2. Now we're going to eliminate this 7. Okay, so as you could expect, -7 times the second row, add it to the first row, replace that first row. Okay, 1 times -7 plus 7 is going to be 0. 0 times -7 added to -5 stays -5. 2 times -7 plus 19, that's -14 plus 19 becomes a 5. So what we get 0, -5, 5. Now divide that top row by -5. And then just for good measure, I'm going to swap rows 2 and 1 just because, again, typically you don't have to do this, but I like to do it just because it makes it look nicer. And we're going to see in the next section um, what we like to do is make this look as nice as possible and always have the same look, or at least as close to the same look as possible as that we can. So what we have there, like I said, is x1 has to be 2 and x2 has to be -1. All right, so if you are asked to write the solution, x1 is 2, x2 is -1. All right, or the solution, if you wanted to write as an ordered pair, would be 2, comma, -1. All right. So that's how we would use a matrix to um, create equivalent matrices. Use the augmented matrix. We create what's called equivalent matrices. They're not equal matrices, but equivalent because they have the same solutions. All the way down until we have a matrix which basically reads off that it gives me my solution. So it reads in a way that gives me my solution. Nice and yeah, compact. So using these elementary row operations is a big part of simplifying, creating equivalent systems of linear equations. And again, we call those equivalent matrices when we deal those. But the elementary row operations are the big things. We can use replacement, we can swap rows, and we can multiply or divide by any number. Multiply a row by any non-zero number. Okay. All right, so that's basically 1-1. Now you have the tools to write augmented matrices, write coefficient matrices, use that elimination stuff, use elimination in the matrix sense, which are just the elementary row operations, until we get solutions to a system of linear equations. All right?